Hello everyone. I hope I'm audible. Can anyone confirm that?
Yes, Lalit, you are.
Okay, yeah.
Good evening, everyone.
Yeah. So so we'll start today's discussion, which is based on week six lectures for the computer vision and image processing course. Okay. So as we always do, we'll just briefly go through the lecture, what was taught, and then we'll start with the question. Okay, so what was done for week six? How did it start? Anyone tell me? Anyone? Okay. So started with frequency domain filtering. So in the previous week, we saw how to filter using time domain. That means we convolve a specific uh, time domain filter onto the image, and then whatever output we get based on the weights, we can say it's the filtered image. It can be low pass, high pass, band pass, band stop. The equivalent was done at the start of this week, of week six, where we started off with the Fourier transform of the filter, and then we use the very useful property of Fourier transform that convolution and time domain is equivalent to multiplication and frequency domain. So based on that, we were so it's easier to multiply things than doing convolution. So we generally take Fourier transform of the input and the filter itself, and then we try to and we just multiply the filter with respect to that transformed image. And whatever we get it, we do an inverse Fourier transform of it. That's the core idea out there. Okay, so there were a few low pass filters that were given. One is the ideal low pass filter. What was the disadvantage of ideal low pass filter? So ideal low pass filter just considers some frequencies within a small range near zero, and it just cuts off other frequencies abruptly. Anyone remembers what the disadvantages are for the ideal low pass filter? Anyone? Okay, so it has the ringing and blurring effect, if everyone remembers it. Low pass filters generally have blurring effect, which is fine because it removes the high frequency component, which is same as blurring the image, but it also has ringing effect because you abruptly stop all the frequencies after a particular range, right? So once you stop it, for instance, if I so if someone remembers, then this is how it looks.
Yes, yes, sharp cutoff.
Yeah. So this part is allowed, and the other part is not allowed outside this circle. So given this, there is sharp discontinuity out there due to which you have the ringing artifacts out there in the output. of the filtered image, rather the filtered image. So, so we would generally not like to get those ringing artifacts because they are uh, unintended. So then we move on to the Butterworth low pass filters, which are more smoother actually. So Butterworth low pass filter will something 2D. It's, I mean, you have, if you have third axis here, then it just falls off smoothly instead of directly cutting off abruptly as here in the ideal low pass filter. So once we have this Butterworth low pass filter, we observe that, of course, now Butterworth low pass filter has a parameter called the order of the filter. So the order of the filter matters depending on how close you are to the ideal low pass filter. If the order of the filter is high enough, then it is very close to the ideal low pass filter. Else it is, yeah, sorry, someone saying anything? Okay, continue then. So yeah, so if the order of the filter is very high, it is very equivalent. It's almost same as that of ideal low pass filter, and you still find the ringing artifacts. But it doesn't occur when your order is low enough, maybe one or two. That's what people generally use in practice. Given this, then we have our famous Gaussian filters. Gaussian filters will also look like this, if I say correctly, but yeah, the function itself is different. So given that this function will be different, it has some nice properties with respect to Fourier transform. Does anyone remember that? So Fourier transform of Gaussian is what? Fourier transform of Gaussian is Gaussian. Fourier transform of Gaussian, if you have x here, so it will again be a Gaussian with some mu and sigma. Then it will be some mu prime and sigma prime instead of mu and sigma. That's it. And it's in the frequency domain, so you have to change the variable u. Fourier transform of a Gaussian is a Gaussian. So that makes it very useful for practical purposes because you don't explicitly have to uh, take a transform. You have an analytical expression. And once you use that, you can use it as a low pass filter for your specific image. Okay, so given this for Gaussian low pass filter, you don't have ringing artifacts. So, well, less ringing artifacts, I would say. And of course, less blurring because as you see, the weights are more concentrated towards the center, similar to Butterworth. So it has less blurring. So this is the best among all the three. This is the best among all the three. This is the medium, but this is the worst in terms of performance. Performance means we don't want ringing artifacts and we don't want too much blurriness. Some amount of blurriness is fine, but we don't really want too many details to be lost. Okay, so given that we have this, what else? So yeah, we can use Gaussian filter to enhance the text that was given, that example was given in the class. And then we moved on to the ideal high pass filters, where uh, high pass filters is one minus of low pass filter, which we already saw for the case of in time domain. We saw this already in the previous week, and it still remains the same here as well. So you have equivalent Butterworth high pass filters and Gaussian high pass filters. And you can use high pass filters to actually enhance the specific edges or high frequency components, as they say, of the image, so that you can have a clear distinction of the boundaries or any other specific uh, transitions out there in the image. And Laplacian operator is also a high pass operator, which we saw for the case of spatial in the spatial domain or time domain. Given this, then we have band pass, band stop filters, and the specific one that we were interested in is homomorphic filtering. Does anyone remember what is homomorphic filtering? Why do we know this? What is the aim of this filter? Low pass and high pass, we remember that for low pass, generally you want to reduce noise. For high pass, you might want to enhance the edges or some other features out there in the image. But what is homomorphic filtering? Why do you want to use it? Anyone?
It is reflection and actually image is a construction of reflection and illumination.
Okay. Okay.
So we from there we are defining a filter because if you take the Fourier transform, that is then we do a convolution, then we take a log, then we take a, uh,
Why do you take log?
to avoid convolution in the frequency domain.
Uh, Really?
Basically, the filter works with only with the illumination or reflection because illumination, reflection, I
Okay.
guess.
Okay. Okay. You are not exactly right, but fine. Anyone else? Since I gave the formula there on the screen, anyone else who can interpret this? What is illumination? What is the illumination component consists of?
Illumination is it is coming from the external source, correct?
Light source. Yes.
Light source, yes.
Yes. So
It is coming from. See, illumination is almost constant. It won't vary much,
hmm
and
okay.
reflections vary.
Okay.
So the idea of the filter is working with reflection to do the remove the noise.
Okay. 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 So the whole idea is that with different illumination, we can have different color images, right? If you remember, there was an example in the lecture where you see that just changing the
Okay.
illumination gives different color images out there. But
Okay.
the point is, we want to know the true color of the object. So how is it
Okay.
possible? So if we can decompose the image as illumination part and reflection part, well, the reflection part is because of the object, but the illumination part is not because of the object, it's because of the light source. Now, if someone uses an old lamp, tungsten lamp, then your image will contain more of red or rather orange kind of color. But if someone uses an LED, white LED, then you can see that your image is kind of too bright, whitish kind of image. So that is the illumination part, which is kind of constant for almost the whole image. You can safely assume that. But reflection is a property of your surface. As we saw, there are diffuse surfaces, diffuse or Lambertian surfaces, but there are surfaces which are shiny as well, like mirror-like surfaces. And there are things in between where BRDF is constant. It doesn't depend on input output directions. So we did that in the radiometry section out there. So yes, so given that idea out there, we want to get now decompose the image into illumination and reflection. So once we can decompose it, we can hope to actually get an image which is independent of illumination. So here the aim is to get an image independent of illumination. So independent of illumination means you want to get the true colors of the object. That is getting true colors of the object. Okay. So this is the main idea. Okay. Given this idea, so someone proposed this specific model that okay, it's the multiplication of illumination and reflection, which I mean they arrived at after multiple experiments. So given this model, now someone said that we take log. So once we take log, you can easily see that log of this left hand side will make this multiplication into addition. And once we have things as an addition, we can try to somehow get an estimate of this illumination and reflection component, and we can then get this thing out of our context. So what do you think? Since I said illumination is almost constant, what kind of frequency information will it contain? Low or high?
Illumination is constant means it's DC, correct? Almost
Almost
constant.
DC, but
Constant.
not just DC in general. It will
Low,
contain
low.
low.
We can consider.
Yeah, in
Low
general, it
frequency.
yes, yes. So it will have the low frequency uh, information, and the reflection will be the opposite one, where it will have the high frequency.
Cycle.
Yeah, because if you see, for instance, a wooden surface, right? It's not constant everywhere. It depends on
Yeah,
what
yeah,
how the wood is cut, right? So there are patterns out there on wooden surface. So these
yeah.
things come under reflection. So once you have the specific model, then you can just, if you do a low pass filter, you can just remove the illumination part and the reflection part stays out there. Once you have this, now you can analyze the object the way you want. So that's the whole part of homomorphic filtering. So you try to make it as independent of illumination or light source as possible. Okay, so given this, we'll move on to the next one. So yeah, the main thing is you can also have multiplicative noise. That's one of the application for homomorphic filtering, which works pretty well, at least for the case of multiplicative noise. But it's in practice, it's very hard to know whether the noise is multiplicative or additive. You have to make assumptions to get started off to what filter you use. Okay, given that, then we have Wiener filter for image restoration. Why the specific Wiener filter is required? Anyone? We have so many filters out there.
Minor filter. It's,
Why do we need one more filter when we have so many of them?
so filter. My understanding is depends upon the situation. They are using different filter.
Yeah, that is true. But then what situation made us, or rather made them discover this new filter called Wiener filter?
This is the something reflection or
So, okay, there is no reflection out there, but there's again some sort of multiplication. Not
mirror.
exactly multiplication, but some
In the
sort.
example, they have shown some mirror reflection or something. So that is removed.
At least I don't remember. I don't think that was an example for Wiener filter. So what is the basic assumption? Like we had this basic assumption here that for homomorphic filter, you can multiply illumination and reflection to get the final image. What is the basic assumption for Wiener filter? So basic assumption always drives how to approach the problem, especially in engineering. So what is the basic assumption out there for Wiener filter? So if this is your degraded image, this degraded image is obtained by some convolution with some filter. Well, this filter is a degradation filter, and this is your original image. Okay. So once you have this specific model out there, that your degraded image, what you actually see, has been degraded by some filter out there, which was convolved with the original image. Then you can then you can actually solve. Uh, then you want to solve what do you want to do? You want to minimize the MSE loss, mean squared error loss, which was, if I remember correctly, it was given something like f of x comma y, which is the input, uh, not input image, sorry, which was the original image, and then this is the estimated image. Mean mean means yeah, it's integration. So this is the mean square for the continuous images. Of course, you have if you have discrete version, then you can just take summations instead of integration. So given this, well, mean square error is a specific loss, and it is applicable only when the degradation filter is Gaussian. If your degradation filter is not Gaussian, then you generally cannot say that the Wiener filter minimizes the mean square error. It can minimize something else, but not the mean square error. So that's the core idea of Wiener filter, that you have an image which was degraded by a filter h of x comma y, and then you get a degraded image based on the specific minimization of mean square error. For the Gaussian case, you can have some nice formula out there how to get the filter weights out there. Okay, so that derivation was done in class. Here we are just going through, so I won't revise that. And then, of course, now we have all these filters and all. Now someone will say that how to measure which image is better, right? Now, perceptually, images can be seen like, okay, it feels good, it looks good to me, but how do you quantify it? So, image quality metrics is something that was also discussed in the class. The first is the simple error. I mean, if you have this original image and if you have this estimated image, then you define this error as this. And mean squared error is take the mean over all pixels. So there is double summation over I and j, and m and n is the size of the image, m cross n. And then what do? You just take the squared differences of the pixel. Yes. So if you have read any of these research papers, then you would know that this is a very commonly used metric out there where mean squared error is reported, or even root mean squared error. So root mean squared error is just taking root of. So why root of MSE? Because this will be in the same scale as out of the image intensity values. That's why we take a root. And then, since image is a signal, so it also has a signal processing. It can also use the metrics used in signal processing, which is 10 log 10, the original image, the energy in the original image, which is uh, just the amplitude squared at which is just the amplitude squared upon the noise. It is signal to noise ratio. So as the name suggests, signal, this is the original signal part, the original image, and whatever is the noise that is coming from whatever we estimated versus what this is the estimated one f hat of x comma y and what the actual image was. Again, the summations are the same, and you just take the square of it. And someone said that okay, this we'll try to simplify it with peak signal to noise ratio. So you actually take the maximum value out there instead of taking just the instead of taking summing over all the pixels, you can just take the maximum value since we don't know the original image in practice. So it will be like 255 squared into m into n because there is summation over the constants, and this part remains the same. This part remains the same. So this turns out to be 20 log 10 if you remove the squares out there, 255 upon RMSC. So why did I write 255? Anyone?
That is the maximum of grayscale value to
Yes. So there's a big assumption out there that we have 8-bit images. For 8-bit images, the maximum, L is what? 2 to the power 8, which is 256. So maximum it can go is 255, right? That's a big assumption out there. Okay. So once this was done in the classes, then we looked about the color image processing. So color image processing mostly is about how we perceive colors. Uh, we generally perceive colors between 400 to 700 nanometers, and our different parts of the uh, eye respond to the colors differently. And also, not all wavelengths, we are not receptive to all wavelengths equally, in the sense that some specific wavelengths we can easily see, but some of the specific wavelengths we don't really perceive it to a good extent. So, of course, there are these biological aspects based on which we had uh, color models defined in our case. So I'm not going to discuss the biological aspects since it was done in the lectures. And yeah, I'll just go through the color models. The first one is the XYZ color model. If someone remembers that, so that's a transformation. So all these color models are generally a transformation from RGB to some other color model. So some of these color models are uh, inspired in the sense that we are able to focus on some colors more than some other colors. There are a bunch of color models. First is the XYZ color model, then there was chromaticity diagram, if someone remembers that diagram looks something like this. So somewhere in between there was white, here it was green, red, and blue, something like this. And based on the distance from here, you define saturation. So saturation 1 means you have reached the border, and hue is all, almost similar to what the angle is with respect to the red color out there. So hue is the angle, saturation is what? The magnitude of the vector. Magnitude of the vector. So yes, of course there is the basic RGB color model which we call as complementary colors. Well, in practice, we know that in nature there is no complementary colors as such. It's just based on what how humans perceive, we call it complementary color. So one can write these RGB color model. This is XYZ in general. This is RGB color model. You can always take a cuboid example out there where one of the extreme ends. You can take this as red axis, you can take this as green axis, you can take this as blue axis, and this will be mixture of two, mixture of all three here. So this will be white and this will be black. Here the mixture will be of red and green, which is what? Anyone? Red and green mixes to yellow. Red and blue mixes to cyan. Oh, no, not cyan, sorry. Red and blue mixes to magenta, and blue and green mixes to cyan. So given this, so we generally think of working in the RGB space, but equivalently we can also work on the cyan, magenta, and yellow CMY space, right? So where do you think why did we develop these two systems at first place? Of course, now you need one color model to actually, for instance, display or print things out there. So one color model is fine, but why then the other color model exists? This cyan, magenta, yellow. Anyone? So anyone can tell me how can I get these values of cyan, magenta, yellow? So assume that these are the corners of a cube. So this is 1 comma 0 comma 0. Maybe this is 0 comma 1 comma 0, and this is 0 0 1. So can anyone tell me how can I get CMY with respect to RGB? So what is the black point? Black point is,
It's
Oh,
000.
yeah, origin
000.
0 0 0. White is,
111.
yeah. So now can you clearly see how to get cyan first? What is the
cyan.
coordinate of cyan?
Uh,
It's 011.
Yeah. So how can you get it from white? So white is 111. So I'll just write it 111 minus whatever the red component you have. So if red is 1,
100
100.
so if red is 1, then 1 minus 1 will be 0. Then this you get the cyan component as 0, 1, 1, right? What about magenta? What is the coordinate for magenta?
101.
Yeah, the y-axis
Yeah,
has been squashed. And for yellow, it is 110.
110.
Yeah, right. So if you are able to get these coordinates easily, then you can obviously get this specific relation out there that for cyan, you just remove the red component. So removing red component squashes it here. For magenta, you squash the green component. Since the green axis is this, you squash it here. And for the yellow one, you remove the blue component. You remove the blue component. Okay. So hopefully that's intuitively clear to remember now. So given these color models, okay. So where would you like to use RGB and where would you like to use CMY model? So I give you two options. Okay. One option is a white paper. You want to print something on white paper. The other one is screen monitor, which is a black screen monitor. So which color model do you want to use to represent colors on these uh, devices or paper? So let's start with
red
monitor.
paper RGB.
For paper, you want RGB, okay. And for monitor,
Very wait. Cyan. Oh, no, no. In the printer, we use cyan. I think the
we are saying for printing, you will use cyan, magenta, yellow. Yes.
Yes, but the refill ink usually yellow, red, blue, I think.
Okay,
Yeah, I mean,
refilling is
again,
quite
cyan
complicated.
and yeah, yeah,
Refilling is complicated. I will not go there. But anyways, I'll give you an example how it works.
yeah, yeah, yeah.
Anyone else? So everyone agrees with what he said that for paper you want to use cyan, magenta, yellow.
Actually, for printing devices, we use CMYK. So cyan magenta. Yeah.
Ink they are selling,
So
not
K is
respiratory.
for black. CMYK
Okay,
model we use for
okay. Let's
printing.
remove K for now. I'm just talking for these two models. Assuming that you can get K with CMY or RGB accurately. That's done for practical purpose, which is completely fine. So for printing, everyone is saying cyan, magenta, yellow. Why not RGB?
Because RGB means we have to use for everything. We have to use all the colors. But if we use cyan, magenta, blue means the
They are
ink maybe
complementary
is
colors, right?
yeah.
So I'm just what this equation says is like if I use RGB or CMYK, they are equivalent. Of course, you have to use it in a reverse fashion. Yes, you
Hmm.
can use either of them, right? But then why any one specific one? So
Yeah,
you
that's what.
people saying cyan, magenta, yellow, but why? Because you need to subtract colors, right?
Okay.
You want to subtract colors. You have a white sheet. White is 111.
Mm-hmm.
So subtraction is done by CMYK model, CMY model. K is okay, fine. So if you ever read newspapers, they actually put that dots, four colored dots on the bottom line. So that's specific to CMYK model. They never use RGB out there. Since you have a white sheet out there, you have to subtract colors. You don't have to add colors from white. That's how the motivation comes. Why CMY model is. What about RGB? What about screens? Screens are black, right? Yes.
So the
Screens
gray
are
level we got to change. Yeah?
no, that's okay. But screens are black, right? So
Yes.
that means everything is 000. So you need a negative model out there. So once you add colors, for instance, R and G, you get some other color out there.
Mm.
So you have to add colors to produce colors there on the screen. So use RGB model on screen. But when you print, generally speaking, you use CMY model, or CMYK, the extension of CMY model. So that's how they were initially developed. But of course, now things have changed a lot. Uh, but most of the devices still prefer this specific principle, what I said now. Monitors use RGB and CMYK models are used by printers. Okay, so I hope the motivation is clear because it's very hard to remember such models, why they exist and all. But I guess if these kind of motivations are there, at least for me, it becomes very simplified to remember such things. Okay, given this, we then that was then HSI model was introduced where H is hue, H is saturation, and I is the intensity. So given that HSI model, you can if you remember the diagram from the slides that there was with these specific models you were dealing with cubes, but then now you can convert it into a cone kind of structure like this, not exactly a cube. So where this was the intensity part, and wherever the circle lies there, different parts of the circle mean the different colors out there. And if you are less than that, your saturation is low, and there is a reference point called red from here you measure angle, which is the hue. The same thing, but it's just that now you have a better way to represent this color, which is the hue saturation intensity model. So once you have these models, of course, now you can convert colors from one space to other space, which is fine. Why do you want to color? So one more specific intuition, which is also mentioned in the lectures, is that when you have color images, the properties are kind of different. Each pixel has now three channels, for instance, for RGB, and they are interlinked. It's not that they are going independent. So you might want to just work with the intensity part and not change the color of it. So the intensity, so once you have the intensity part extracted from there, you can just process the intensity part and keep the color part same, and then merge them together to get the refined image or processed image. Processing can be any kind of processing, low pass, high pass, or some other sort. So that's the main intuition why these specific models now HSI model was introduced or why IQ model was introduced. Well, why IQ was for TVs actually, but anyways, so these models actually try to separate each of this intensity part from that of the color part. So which was again the same basis why homomorphic filters were used. Not exactly, but to some extent, yes. Okay. Given this, there were other models, YCBCR, and they are used in color image compression, which is fine. And then CI Lab is one of the most widely used color model in general to for practical purposes. But then now, as I said, that these are ultimately vectors. Pixels are now contains vectors of data instead of scalar of data, as we saw for grayscale images. So there are a few problems with if we do if we treat each channel of the color independently. Like one of the examples given was that we have false colors out there. That means the colors which never existed in the image, you tend to get those colors out there, which is of course not natural enough. Since color is more about perception, we would like to keep it as close to what we perceive as possible rather than randomly assigning colors. I would not say randomly assigning, but assigning colors which don't look natural out there. So given this idea, so whatever filters that were developed for color imaging were took all the three channels. For instance, if you have RGB channel, they took all the information from all the three channels and then tried to come up with a solution rather than just doing each channel individually. Okay, so which includes histogram equalization, one of them, and the other one is vector median filtering that was also given in the lectures, if I remember correctly. Yeah, that was also given in the lectures. Okay, so given this, there was the last lecture on segmentation, where what what is the main aim of segmentation? Anyone?
uh, extracting homogeneous information.
What is homogeneous?
Homogeneous means um, same
Alike pixels,
alike.
Pixels
grouping
is
alike pixels.
similar
Or
in some sense, yeah. So the similarity is generally given by what is the intensity value of the pixel for a grayscale image, for instance, or maybe the color values. How similar are they? Okay. Someone said shape, texture, motion. It's fine. For the course, we are using just similarity of color values or grayscale values. So if you think that some colors are similar, maybe they belong to similar object, for instance. Like a table will be the same color, it won't be similar to that of the wall color in general. Of course, now there could be cases where they are same, but in general they are not same. And maybe if you have a toy out there, the toy could have some very bright color like yellow or something, but your table could be dark color, so you can easily distinguish that there are different things. So how to actually make computer work or realize that okay, there are different things out there. So one of the ways is the segmentation. Yes. So the basic idea of the segmentation is that you have what? The segments are such that there is no overlapping between the segments, and all segments, when combined, gives you the original image, right? So the first thing is segments will always be like this. This is right. Segments can never be like this. This is wrong. No overlaps. And the other thing is segments will always cover the whole image. It can never be like this. So here everything is a segment. Here, but here if someone says that this is a segment, then this is wrong. It should cover the whole image. They are the basic assumptions when you actually try to do the segmentation. And this actually helps to simplify the problem a lot. Okay, so given this, now there should be a metric which was specified in the lectures as predicate. So that metric says whether some pixels should be in the same region or they should belong to the other region. Okay, so we'll do an example there in the question, so we don't I'll not go through it now specifically. But then there are other ways of thresholding is like you can also segment image while by thresholding. One of the ways is like get a threshold. You have the histograms of gray values, you get a threshold and then fix that threshold. Less than that belongs to one part of the image. Greater than the threshold is on the part of the image, which is generally useful if you want to separate out foreground and background. And hopefully the foreground and background are not far away. In the sense, oh, sorry, no, foreground and background have different colors. If they are of similar colors, for instance, someone has seen this camouflage pattern, right? Generally used by army or navy. So when they go into the forest or even from the skies, when you see this camouflage pattern, they may planes, it's very hard to detect just by seeing it. So those we assume that they are quite separable enough, and we don't use such specific cases. So that is one of the case, and maybe then you can just approximate the whole histogram by two Gaussians out there and get the best possible threshold with that Gaussian modeling. Or you can also do region growing that where you specifically choose a pixel starting pixel and then you see which pixels are similar to that specific pixel and then uh, yeah, grow on the regions out there. So we'll also do an example of region growing. One more example is the quad tree example. So it's generally seen that for many images, most of the image parts are similar. So you can actually create a quad tree. What do you mean by quad tree? So does anyone know quad tree? So the quad here refers to means you are dividing it into four chunks, right? So everything is now divided into four chunks. Now you can choose whether to divide this as four chunks. This may not require division. This might require division. So we'll again divide it. And after that, maybe we might reach a stage where we don't need any more divisions. So quad because we are working on 2D space. In 1D space, 1D equivalent is what? Binary tree. Yes. So in 1D you have just two. You can divide at max with two. There will be two subdivisions out there in the binary case. Okay, so for quad there will be four subdivisions at max. So given this, I guess we also have an example of this and the questions. We'll do that. And the one more topic given was the active contours, where you try to get some idea of what the contour of the image is. For instance, if you have an image like this, maybe there is a sphere in the image or circle in the image. Even if you image a sphere, you will ultimately get a circle out there. Okay, so if you are imaging and you get this circle out there, and if you start a contour like this, this is the active contour, and this is something that circle that you want to detect. So given that, you can actually this turns out to be an energy minimization problem. With this energy minimization problem, we can minimize it. We can minimize the sum of energies, which is internal and external, which converges to this circle now. Okay. So there are different parts of the energies that we'll again go through once we have the questions out there. The other one is the watershed algorithm. That given that you have a nice what do you say? So if you have some nice intensity graph like this, where this is zero, this is maybe you can take this as zero, you can take this as 255 as in the example. So you try to fill water from the below. So once they are almost near the point where they are going to mix, you identify where they are going to mix, and you can mark it and not allow them to mix. So you can construct dams out here. They call this specifically watershed line. Actually, this is the watershed line. So this is a very physics inspired example that you are able to fill water from below, and then you get the segmented parts of the image. Since you assume that this is like a loss landscape out there, you can actually use physics to make things work out. And the last thing that was taught, if I remember correctly, is the k-means algorithm, k-means clustering. So k-means clustering is actually very important, not specific to image processing, but also in general if you are doing data science or machine learning kind of problems. So this also comes under unsupervised learning, because there is no supervision out there that what is the correct cluster out there for you. So you're given a bunch of points, maybe set of points are here, another set of points are here. Now you want to cluster these two out there. Given this problem that you have, you would use the k-means clustering algorithm out here. Okay, so yeah, it's also used in images and it proved to be very effective. Okay, so I guess these lectures are slightly lengthy. That's why it took with many small points out there. So it took some time to discuss, but now we can start with the questions, specific questions. Of course, we'll again go through the specifics as we come across the questions. So hopefully things will be clear then if it's not clear now. Okay, so we'll start off with the first question. Yeah, so we don't have any question on frequency domain filtering. We'll only have questions for color image processing and this image segmentation. Okay, so if anyone remembers what is region splitting and merging, does anyone remember that? What is region splitting and merging? Well, I did tell it here, but
Yeah, quadtree.
yeah, quad tree
Mm.
based algorithm is the region splitting. So here we are assuming quad tree based algorithm. So yes. So, okay, people are still joining. Okay. Yeah. So given this, specific question. They want to apply region splitting and merging to see how many isolated pixels are there for a threshold value of 1. So what is isolated pixels? Anyone?
So, with the neighboring pixels, if we compare the pixel value, uh, it is not matching with the threshold value, or that is greater than 1. Here, the threshold value is 1.
Okay, okay, okay. That is fine. But what in general? Anything that you could say? So
The
oh
isolated,
yeah,
isolated,
It is
basically,
isolated, yeah.
yeah, basically the threshold removes the background, and isolated pixels are the object.
not
Uh,
really.
it is like a
Isolated pixels.
homogeneous pixels. Actually, they are related to each other.
No, actually just said the opposite. So
So,
these
if
pixels
suppose the
are
pixel value is 1 and the neighboring pixels are 1, 1, 1, then we say that it all are homogeneous.
yes,
If something like that,
Yes,
right?
yeah, but here the point is they cannot be merged into any of its neighboring pixels. So they are not merged in any. They are not a part of big regions. They are just one pixel region out there. So ultimately, what we are trying to do is segment the image, right? That's the
Yes.
whole idea here. Segment the image in a meaningful sense. So meaningful is because we are doing mergings. That's why we can say that we are doing it some meaningful sense. But now, if someone says me that you can clearly see here, right? This is one of the uh, region
isolated. So, one,
regions,
two.
not isolated. This is isolated because it's very quite different from the nearby pixels. This is
Okay.
also isolated because it's somewhat
Isolated. Yeah.
different from the nearby pixels. So yeah, they will actually prove it using the specific algorithm called preference algorithm. So how to proceed?
So first divide this into
Why?
four,
Why do you
right.
want to divide?
So
Just because
apply
algorithm
quad
says
tree.
no, no,
Quad
that's
Apply
okay.
tree.
quad.
That's okay. Just because algorithm says, will you start dividing it? Do you have to check something?
Yes.
What is it that you want to check? Algorithm says divide it in. We want to divide it into meaningful parts. Now, what if all of these contains zeros and ones? There is no 5, 6, 2, 3, nothing. So if I give you an example, I'll just take a smaller example: 0, 1, 1, 1, 0, 0, 1, 1. And since if you see that the threshold value is 1, all of them should belong to the same uh, region, right? So there is only one region. Yes.
Yes, yes,
Then you won't don't want to divide it, right?
yes. So you need to check the threshold value. If any
Yes.
pixel has a um, value
Correct.
greater than threshold value, then you have to divide.
Yeah. Yes. Yes. So that's the core idea. First, you take the full image out there and then check for the threshold value. How do you check for the threshold value? So someone said that you have threshold value of 1. That's given in the question, but how to check for the threshold value? What is it that you want to check here? What is the homogeneous definition of homogeneity in this context? It is dependent on pixel values, but what is it exactly? So you can think of it like this: maximum value in the specific uh, region. So I have not divided into regions, so there is only one region. Max value minus min value in the region is less than equals to the
Is less
threshold.
than equal to threshold. Yeah.
Threshold given here is 1. Yeah. So first, given the whole image, you should check whether this satisfies or not. What is the maximum value? 6.
6.
Minimum is 0. So it is 6, which is greater than threshold. So So now, given that you have this idea, okay, this image is not that similar, or this doesn't have a single homogeneous component. Now you can just try dividing it. So okay, now since we have this quad tree example, we divide it with a quad tree based example. Right? So we divide it to four regions. So given these four regions, now what to do? We'll check first region. Region 1 satisfies this.
Yes.
Maximum, minimum. It satisfies. Region 4.
Yes.
This also satisfies. Fine. What about this?
This we need to divide.
Yeah, it doesn't satisfy the threshold out there.
Doesn't.
So it's like
Yes.
2 minus 0 is 2, which is greater than threshold. What about this?
Same. We need to
Same.
divide.
We need to
Mm.
divide. So what we again use the quad tree specific example. The algorithm says us, oh, divide it again. Fine. Okay, we divided it. So now we have individual pixels out there. So ultimately, we have these many divisions. You can't divide it more because now these are individual pixels, right? Can't divide it more. So given this, what is next that you want to do? Hmm? You're done with splitting, right?
Yes, yes.
So
So
now
we need to merge
merge.
the homogeneous
Yeah.
Totally,
segments.
we from here we get to three segment parts.
Okay.
This algorithm will give three segment part.
Three
But
segments. How do you say that? I see so many
because the
segments out there.
first
One
first one is a threshold 0.
threshold zero. No, don't change the threshold that's given to you.
I mean, the max value minus min value is 0. That one.
Actually, okay, this is fine. So that's why
Yeah.
you have so many regions, right? This is one, and each individual
Yeah.
ones are also a region. So ultimately, you have 4 plus 4 plus 2, 10,
Hmm.
10 regions out there. But now we need to start merging things. So how do you merge things?
So the part which is homogeneous, we need to merge, or which satisfies the condition of max value minus mid value less than
Yeah,
or equal to
yes, yes,
threshold.
yes.
So
So that
that part
whichever
we
satisfied this homogeneity condition, we
yes.
will use homogeneity condition. So yes, again while merging, we have to make sure that we are in the homogeneity. We are using the homogeneity condition. So what if I take a specific example like okay,
Because to avoid the overlap,
yeah, yeah,
same
merging means it won't overlap. It's fine.
overlap. So same part should not be divided into two parts, right? So we have to
Yeah,
make
okay.
sure we have segmented the image appropriately. So
Mhm. Okay. Yeah. So now if
because of
I
one
yeah, yes,
because so one same homogeneous image can be fall between two quarter, actually 2 quarter or 3 quarter,
yeah,
that
yes,
initially we don't know. After merging only we get.
yeah, that is right. So while merging, as yeah, someone said that we have to make sure that we still have this homogeneity condition satisfied. So given that I drew a violet box out there, you think we can merge this?
Yes.
Why? This violet box?
Yes, we can merge this.
Why?
But
Then
that
the
one
up
one
the
they won't say that quarter itself it won't satisfy
Okay.
this threshold value, correct?
Okay. So someone
As
said yes.
algorithm, we should
I
ignore
want.
it.
Yeah, yeah. So someone said yes. I wanted to know their opinion. Why did they say yes?
no no sorry I make it clear.
So
We
before
should not
merging,
say. Yeah, got it.
so before merging, homogeneity wise, you have to make remove those regions, and remaining region we have to check whether we can merge or not.
Yeah. So we divided it to the maximum possible extent. So
Mm-hmm.
that's already done. So now I just
So
considering this here violet box out there. So can we
So
merge
while
this?
merging also here, we will get two segments it seems. One
Okay.
one 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 and 10 and 6656 will be second segment. Like that we will get two
Then it does
segments.
that merging doesn't make sense, right? If we have again segmenting it, then there's no point merging it. Yes.
Okay.
So just check this homogeneity condition. So what is the max value in this violet box? 6. What is the minimum value? 1.
1.
So 6 minus 1 is greater than threshold, right?
Yeah.
So you can't merge this. So don't
Hmm.
merge.
Yes. Hmm.
What about this one?
Yeah, this we can merge.
Because it's just 1 minus 1, which is 0, max and min value, which is less than threshold.
Right.
So given this, we can merge this. Okay, fine. What about the next merging? So now I am currently
Yeah.
here. What about this? Can I merge it?
Yes. That we can.
Yeah, because the homogeneity condition is still satisfied. Can I merge this?
Yes. No.
No. Yeah, because 2 now. The
2
difference is
minus
2.
0. Hmm.
2 minus 0 is 2.
Hmm.
Okay. What about this? Can I merge this?
Yes.
Okay. Yeah, because everyone is 1 or 0, so it's fine. What about this?
This one also you can merge. Yeah.
Yeah. Okay. So given this, what should be the answer? What was the question? How many isolated pixels are there?
2 and 3. So 2 is answer.
2 and 3.
Yeah. So the number of isolated pixels is 2, right? So these are the specific isolated ones, and
Yes.
so the number are 2. That's fine. So someone say that is this the only answer? Can it be a case that there could be different isolated pixels apart from 2 and 3? Yes, no.
Sorry, what is the question?
So the question is that we now deduce that 2 and 3 are the isolated pixels. Is there any other way that you can see when 2 and 3 are not probably not isolated pixels, but some other combination are isolated pixels? Is it possible? So if someone remembers, I started by merging this first, and then merging this first, and merging this, and then this and this, right?
Yes.
What if I just change the order? Instead of merging this, I merge this first, this specific thing, right? Then the difference is 2 minus 1, which is 1, which
1.
satisfies the homogeneity condition. Yes. Then 2 is inside. Then if I check for 0, 2 minus 0 will
Then,
happen. Then 0 won't occur. Yes.
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 So it is dependent on how you go through the image, right? You may not have the unique way of
Yeah.
getting
Yeah.
what are the isolated pixels, but you for this specific case, the number of isolated pixels are still the same. Yes, either 0 or 3 or 2 or 3.
Right.
Yeah. So I mean, whatever way you do for this question, it's the right answer. But it's very necessary to know that while implementation, if you're not expecting, if you're getting something which is not expected, you should understand whether that this condition itself gives you a unique answer or not, because everything is hinged upon this condition. Yes. Okay. So given that, we'll move on to the next question, which is simple, I guess. Any doubts in the first question? Okay. So I guess there are no doubts. Fine, then we'll move here. So we have this K means clustering question. Okay, you have 10 data points out there. You use K means clustering for 2 iterations. The initial labels are this. List out the labels after 2 iterations. So ideally, when you're implementing, are you given initial labels? So So these are the labels for the classes. These are the class labels. You have to, or cluster labels, whatever you would like to say. So someone already gave you that these are the labels for these clusters. Do you think that is it always the case in real life?
No,
Yes. Then how will
they
you?
can provide a centroid also.
Yeah, okay. So generally what you have is no one is providing anything. You collect data, you just have these data points. How will you start?
O- Okay.
How will you start?
We take 3 points. Suppose if you want to start with 3 clusters,
Yeah, it's given that you
you
have.
yeah. So
Yeah.
we have to if
So
we,
the
suppose
first,
four cluster means four random points. 3 cluster means 3 random points. Then we calculate the distance.
Okay.
Based on
Yes.
this, we label it.
Yes. Yes.
We
So if you
associate
have,
with that.
yes. So when you have this uh, specific problem, you always start with three random points out there, but you generally try to keep them spaced far away. I'm giving an
Okay.
implementation aspect. Okay, so if they are far spaced far away, then you can actually converge faster. Otherwise, it will take more number of iterations to get to the final answer. So when you're
Okay.
doing this, make sure that they are spaced far away. You can just check the Euclidean distance between all the 3 points. Maybe just take corners of a equilateral triangle, but the triangle side length should be good enough so that it covers all the points out there. So that's what I mean. Yeah. So a simple example is like this. If I have clusters like this, I have two clusters, for instance, and if I initialize both the points very badly, one point here and the other point turns out to be here, right? Now the distances are quite similar, yes, for both of them. But for this one, it will of course come here. The distance will be smaller. The point is, it will take more iterations compared to when you initialize one here and the other one here, right? So initialization actually matters when it comes to implementation aspects. Okay, so given that, we'll come back to the question. Uh, what is the question? The initial labels are this. List out the labels after two iterations. How do I proceed? Anyone?
How to
Yeah, how to
proceed?
proceed with this question? So you have
so for
some
the
initial labels.
clusters,
Yeah.
the
What is the
the
next step?
first point I considered as a centroid for the first cluster. Then the second, from where the second cluster starts, the first point of the second cluster.
Okay, you're saying that these specific points
Yeah,
will take as central, right?
yeah, at centroid, and then calculate the Euclidean distance, then get the actual centroid, and then the second iteration.
Okay, you don't have to choose any of them as centroid. You have to get centroid using all these four directly.
Yes.
Yes,
So Ci is the centroid for ith cluster is what? Summation over j. What? What will it be?
X.
X. If I call these as x's,
X. Yes.
xi. So here it will be xj. J belongs to class I.
Hmm.
Cluster I.
Number of class.
Yeah, maybe I'll write AI as
Hmm.
ith class. Yeah.
Hmm.
So now if you see there are four things out there. There are four elements for the first class. You just sum the four elements, okay, and take the average it out. Average meaning you have to divide it by the number of elements in the class. Yes. This is the number of elements in the class. This is the cardinality of the set. So given that specific formula, we can always uh, get the centroids, right? So now you have three different centroids. So you don't have to consider anything initially. Since you are given labels out here, just get the centroids by using which points correspond to which class, right? So we will have C1, C2, C3 computed from this. Once you have C1, C2, C3 computed, then what is the next step?
Find the distance for that those 3 points
Yeah, yes.
Uh,
Distance for the 3 points from
from all the
all the
for all
points.
the
all the
pixels.
centroids. Yeah.
Yes. So all these three centroids, you have to get distances now. So x1, what is the distance? X2, what is the distance? Once you have the specific table out there, so you fill values here, right? Once you fill values, what is it that you do now? So you now got to get all possible distances out there. So C1 is some meters away from x1. C2 is some meters. Well, meters, I'm just saying it for namesake. There can be any other unit. C3 is some units away from x1. So after this, how do you choose? What's the next step?
So now we change the label according to the distance. So suppose
Yeah, how do you choose
x1
the
is
label?
minimum distance to the centroid.
Yeah, yes.
So
So
the
if
pixel
you
will associate. Yes.
consider the specific column,
Mm.
what is the minimum value? So choose C with minimum value across column, along a column. So once you choose the C for every column such that it is minimum along the column, so you might get one probably C1, C1 here, C2 here, C3 here, somewhere between C1 again here. So you get these new labels out there. Once you get these new labels, what do you need to do?
Repeat.
Yeah,
Same
repeat. Yes, correct.
loop.
So use
Yeah.
this specific formula out there and then again get the table and then again choose it. So in practice, this is done on a computer until convergence. What is the convergence criteria?
No more. Always has suppose currently associated values should be retained for all the pixels.
Yeah, that
Centroid
means
Repeated.
not moving from one centroid to
so.
another.
Yeah, whatever you have chosen the class in the previous iteration, that should remain the same.
That should be written.
Yeah. So an easy way to check it is what? What's an easy way to check it?
Is a way to
Yeah.
check. No. Uh, that
Yeah.
calculated
Oh,
centroid value will be same.
Yes, exactly.
yes.
Yeah. Mm.
So easy way to check is now if you have very long list of data points, maybe 10,000 data points, you cannot check the class for each of those data points, right? But easy way to check is if you just have 10 classes out there, you can just check centroids won't change. Centroids won't change from previous year. Everyone agrees with this point, right? Both are equivalent. Both 1 and 2 are equivalent. Yes. That means if I check for all classes, the same as checking the difference of the centroids with the previous iteration. Yes. Everyone agrees with this. Both are
Yes.
equivalent or not? Yeah. Because why? If you see this formula, we are just dependent on the elements of those classes. If the elements won't change, the centroids also. Yes. The argument is clear. Fully clear, I guess. Uh, okay. If you have any doubts, let me know. Else we can move on to the next question. So yeah, for this specific question, you have to do it twice, and whatever other classes assigned, you can just check it and replace it with the final class. That's just computation. I'm not going into the algebra part since we are short of time and we want to complete more questions. But I hope the main idea is clear. Okay, I think things are clear. No response from there. So we'll move on to the next question. It is about active contour segmentation. What is active contour segmentation? We just discussed it briefly while going through the lecture, going through the summary of the lecture. What is active contour segmentation?
Contour segmentation.
We just discussed it, right? What is it used for?
This is
Uh, hang on. Okay, so if you remember that, I just drew a diagram where I had something like a circle, and then I had a random curve on top of this, right?
With external and internal energy.
Yeah,
That's
yes, yes, yes. So the random contours, sorry, not random contours. So the active contours, this is the active contour, and this is the object that you want to uh, capture, object to be captured, rather to be segmented. Whole idea is segmentation, but here you have an idea of that. Okay, this is the object, and you want to exactly capture that object. So there you can use active contour. Okay, so this is the original idea. So does anyone remember what does it have to do? I mean, what are the different energy terms out there?
it.
So what is I told something that the E total, which is the total energy, consists of internal and external energy. What is internal energy?
Inside the inside the contour.
So, yeah. So internal energy is defined by the contour, current state of contour, current state, not the final state is the optimized state, of course, but current state of the contour defines the internal energy, which consists of what?
Current state of defined by the
Hmm? Anyone? Elastic energy and bending energy. Yes.
Yes, yes,
Hard to
okay.
recall, right? Okay. So yeah, these things, if you abstractify too much, it's very hard to recall. I'll give you a nice analogy out there. What have you seen a rubber band out there when you try to cover, for instance, maybe a cylindrical object like a jar with a rubber band? How do you do it? You extend the rubber band. Yes.
Yeah.
So
Yes.
when you extend the rubber band, what happens? The elastic energy is trying to pull it back to its original shape. Yes.
Yes.
Yes. And then what about bending? So if you extend a rubber band, for instance, so that with using your three fingers it becomes a triangle, that is the bending energy. So you're bending the rubber band if it wants to come back to its original shape. So that's the bending energy part. The elastic energy is like if you increase the circular size by a large amount, that's the elastic energy part. Okay, so think of it like a rubber band. So this contour is the rubber band, and this is your specific jar, maybe your favorite pickle jar that you want to cover up. So so you actually want to get that specific contour of the pickle jar given this rubber band. Yes. I hope this
yes. Okay.
specific example
Yeah. Yeah.
pretty much simplifies things, and hopefully we will remember it for long. Okay, so this is the internal energy, but what about the external energy? Now we were just fixated with the uh, rubber band, but that jar has some specific shape, right? So it should define how the final state of the rubber band is. Yes, that is the external energy part. So that is defined by the image in the specific case, or the jar, if you can. Here I can write rubber band, and here it is the jar. I love jars and I love pickles, so I do make sure that I use this example everywhere. Okay, so coming back to the question, yeah. So what this external I mean, what is this external energy specifically out there? The external energy is you can define it either using gradients, direct gradients of the image, or else you can take what low pass filtered image and then take gradients. Why do I want to do low pass filtering before I take the gradients of the image? Anyone?
The pixel gradient.
What does low pass filter do?
It remove high frequency.
So
So
any reasoning why you
I
would
mean, um, yeah, smoothing it would do.
same thing? Smoothing, removing high frequency. Yes. So what then what? Any concrete reasoning? Smoothing and all is the effects, but why do you want to do it? What is the cause? So if I have a noisy image, how will the gradients be?
Huge.
Yeah,
Mm,
wherever the pixels are noisy, the gradients will be high, unnecessarily
mm,
high.
mm.
But we know that it's because of noise and we don't want to be influenced by noise. And
Okay.
also our specific
Mm.
external energy should not be influenced by noise, right? Otherwise, we cannot capture the specific object that we want to get through the
Mm.
active control algorithm. Okay, so the main idea is we want to be kind of robust to noise. So we can use we won't directly compute the gradients which are actually noisy. So what we do is we can just do a low pass filtered image and then get the gradients. The low pass filter will actually remove noise to a good extent, and based on that you can do gradient computation on top of that image. Yes, so the intuitive idea is clear, right? So this is how the external energy is defined, and then summing of the two will give you the total energy, which minimize this to get segment object. That's all the idea is. Okay. So I guess the whole procedure is now clear. Although the specific implementation issues will be there. And actually, this question is more about what specific implementation issues you will have rather than the procedure out there. So the first part, it depends on the initialization of the curve in the image. Is it right or wrong?
Right.
Right.
How do you say that?
Because of it, it's elasticity curve.
Elasticity curve, yeah,
Yes.
that's something.
Yeah. So that elasticity is the main. That rubber band is the first one.
Yeah, rubber band.
I,
Okay. Yeah. So
I,
if I
I can't. It's actually understood better than before.
Yes, that was a nice example actually.
okay, that's good. So yeah, if you don't place your rubber band properly, means if it's not around the jar, if it's somewhere here, if the rubber band is here, this is active control, and this is your jar or object. So if your rubber band is here, then assuming that your rubber band is can shrink to a point size, it will just shrink to a point size here. So it won't capture the object. It just becomes a point, right? So yes, it depends on initialization. So depends on initialization. Okay. So this is the first part of the question. Fine. What about second thing? Highly sensitive towards noise. Yes or no?
Yes, that is true.
Yeah, that's why we are taking low pass filters. So assuming that you have some noise, like this could be my object, but there are some sharp spikes out there. This is not the original object. The original object is circular, but you have some short spikes because of noise. Then even if you place active contours, then they will try to replicate the noise as well. Yes, replicate the noise to fit to fit the to minimize the energy. Fine. Okay, yeah. So yeah. So given this, what is so it's of course sensitive to noise. Sensitive to noise. So second part is also true. Both of them are true. I should just start writing here. True. This is also true. What about this? Give over segmentation for complex objects? Yes or no?
No.
Why?
It um, be- because like you said previously there is a spike, correct?
Oh no,
Same thing.
that is for noise. I'm giving an
Yeah, yeah,
example
that
for
is nice. So for it is not depends upon complex or simple, this
really.
algorithm.
Okay. I'll
So
give you a complicated example to make sure that the complex example is there. The complex object is there. Okay. So if you have again taking the circle example, but if light is coming from here, okay, and assume that this is mirror-like surface. So here it is very shiny. Yes. If it is mirror-like surface, and so this is lighting direction. So what you have? This part is very shiny. This will almost be black, right? Because there is nothing, no light being reflected, almost black. And if a background is black, yes, is it a possible case? Real life scenario?
yes, yes,
Yeah, yeah, yes. When you actually go out and see the rocks out there, this part of the rock might be very bright because of sunlight coming, but this part of the rock is very dark. And if it's covered properly, it's almost zero. So you can have some black background out there. So this is actually a real life scenario. So given this, what can you say? What if you initialize it properly as well? This is the
Yeah,
actual
we
contour.
cannot initialize it properly. The contour might go wrong.
Yeah, the initialization is fine, but it's trying to minimize the energy, right? So
Yes.
so the final contour might be like this
yes,
because that's the only shiny part out there.
Mm.
So now can you say that this is this can give over segmentation of complex objects? Yes, that's true.
yes.
Yeah.
Yes.
Okay, what about the last one? Active contour around the object has external energy which measures the continuity of the curve. Active
That
contour
is wrong.
You
has external energy which measures the continuity. Okay, true or false?
False.
False. Why? It's here, right?
yeah,
External energy is
It,
defined by the image and not
mm,
the contour. What they're saying is external energy defined by the continuity of the curve or the contour,
mm.
which is of course a false statement. Yes.
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 Okay. Any doubts in this question?
So, I have one
Yeah.
question, but it is not related to this. So, which segmentation algorithm is mostly used then?
Well, if you ask me that way, then it depends on the context. What you want to segment. As I said, for complicated images, the things can be very complicated. So
Okay. So, it
it
depends
depends
upon
on
the image.
application.
Okay.
So application means, yeah, uh, now if you're taking some uh, roadside kind of street views and then trying to segment a few things, and that will have different characteristics than going into a forest and trying to segment trees there. So
Okay.
everything will have different characteristics, and based on that, to be frank, these segmentation algorithms are fine enough, but they are not super great and not super robust. In practice, there are learning-based algorithms, specifically, I would say the deep learning-based algorithms, which work pretty well for segmentation.
Okay.
At least for the current, if you want to use anything for your project, I would suggest a deep learning based method. Of course, now the deep learning has its own priors, that where the data is trained. For instance, now I said, if you are going in a city and segmenting things, so deep learning will actually try to get the distribution of the city rather than the forest. So if you apply it on a data set of forest, it won't work. So
Okay.
of course, there are all these engineering choices, but overall, if you have a good trained model of using deep learning, it works better than these classical.
Okay.
Yeah. Okay. So
Okay.
we
So
move on to the next question. We have an image patch threshold is less than 3. Okay. Select the region growing output for the seed 2 comma 3. So what is this 2 comma 3? That's the initialization point, and we are starting at 1 comma 1. This is 1 comma 1. Where is 2 comma 3? This is 2 comma 3, right? So what is region growing? Save time.
We look for the
so
homogeneity around
you
like in neighboring pixels and merge that.
you
Yeah,
have to add the neighbor based on the difference. If it difference is less than threshold, you
yeah,
can
yes.
grow it. You grow the
Yes.
region actually.
Someone said homogeneity, which is the right word to use actually. So homogeneity criteria here is what? What is the homogeneity criteria?
The
Difference is less
seed
than 3,
point
less than
value.
equal.
Yeah. So
Sorry,
in general, what would be the case? Again, max minus min, right?
max minus min. Yeah.
Max value minus min value. Ah, of the potential region, I'm saying, not the actual region. Max minus min value should be less than equal to threshold. The same criteria that we looked up. Okay. Yeah. So given this, I will have some. I'll start from here. So now what? Where can you grow?
Yeah,
You
you
can.
can go left 7. We can add.
7 is fine, right? Threshold is
Yeah.
3. Yeah, 7 is fine.
Yeah.
6 is fine. 7 is fine. Then 6 is fine. If you go above 6 is fine. 6 is fine. What about 5?
That
7
is
minus
also
5
5
fine.
is
also.
2.
7 minus 5, 2 only.
So 2. So the whole this part is covered. What about right side? I can add
Yeah,
these two
7
sevens
Again,
minus.
as well.
7. Yeah.
Yes.
The
What
first
about
row.
5? Again, yes. Right.
Yeah, 5 and 7.
Again,
5,
yes.
7,
Right.
6 we can add.
What about 4?
Yes, we can
4
add.
is
7
beyond.
minus 4 is 3. It's just within the threshold.
Oh, yeah, 3.
So yeah,
Okay.
this whole thing can again come inside. So yeah, given this, what else? So this is again my seeding point. I'll move down towards the seeding point. 4 is fine with me, right? 7
Yes,
minus 4 is still 3.
Yeah, yeah, yeah.
4 is fine. What about 6? 6 is also fine.
that is fine.
Fine. 5. What
And
about
another
5?
that side 4 also.
Yeah, that's at 4 also. Okay. What
Mm.
about 3?
3
3
we
is
can't
also fine.
out of 7
Yes,
minus
3 is fine.
3
7
greater
minus
than.
3 is 4, right?
Mm.
Crossing the threshold.
7 minus 3. Okay.
Yeah. Max value, I
Fine.
said, right? Max value of the region minus min value of the region. Potential region. So if you add 3, the max value minus min value will not be within the threshold. So it will go out. I mean, it won't be considered. Yeah. So 3 won't be considered, then 2 won't be considered. What about 5, 6? So till now, what are the ranges that we can consider? 7 to 4.
4.
And 7 to
Yes.
4, we actually covered the whole threshold range. Now you cannot have anything more. Right?
Yeah. Okay.
So here 5, 6, 4, 6, 4, 6, 5, 6, 4. So the whole of this can come inside, right? Because these are between 7 to 4. Yes.
Yes.
So the whole this specific region will again have the threshold value less than or equal.
Mm.
Yeah. Okay. What about here? 5 is fine. 4 is fine with me. 5, 4 is fine. Okay. 0, 3, 2, 3, 3. Okay. 3 is not
We
fine.
can.
What else can you have?
That's all.
That's all.
Yeah, that's all.
0 we can combine 3
Yeah,
to.
0, 3, 2 is fine. Okay. So this is it, right? So your final region will look like this. Correct me if I'm wrong. I think this is correct. Yes.
Yes.
Yes. Yes.
Okay.
I have
So
a small question here.
yeah.
Uh, as it is, we are considering max value and minus mean value should be less than or equal to threshold. What is the role of seed point? Like if we change the seed point, will
Hmm.
this homogeneity will change?
Yes, if you initialize this here, somewhere here, instead of here, what do you think? Then all the values between 0 to 3 will lie, right? Nothing going on 4. Then this region will come up.
Oh, okay, okay. Got it.
Yes, this
Yeah,
region
yeah,
will come up.
yeah.
Yeah. So initialization matters. Threshold
Yes,
also matters. Defining that defines what your specific region is out there. Yes.
yeah, yeah. Got it.
Okay. Okay. Any doubts to this question? So I think it should just give you a sample option. Actually, this is the right option. I'm just giving a since we solved it. So your option looks like this. So this black region is what your connected homogeneous region is, and the white region is the non-homogeneous region. Okay, is this fine?
Yes,
Then
yes.
we'll move on to the next question. Okay, so this is a conceptual question. When we are mixing white color with green color, what are we decreasing? Before that, what is this white green stuff? What is hue? We discussed it at the start of the session. What
So
is hue?
it's the wavelength
Wavelength.
or
Yeah, it gives the color information.
color. Huh. Color.
The color information or wavelength, it's fine. What is saturation?
That amount of uh,
Amount of
color match.
Amount of white color.
Yeah.
yeah, amount of white color in the
White
Yeah.
color.
Right.
Yeah,
specific wavelength.
Amount of white color.
yeah.
So just an easy way to visualize this. If you assume that your colors are lying here, R, G, and B, in this specific representation was given. Let's just move that. But yeah, so given this R, G, and B out there, what is your hue? Hue is actually measured as the angle, which is, of course, here the color information out there. So as the angle goes probably 120 here, it goes to green, 240 is blue, 0 is red, and somewhere in between they are the mixture of colors, the primary colors. So this defines hue, which is color information. And what about saturation? It is the magnitude of this vector. If it actually goes here, it is the color is saturated to the maximum. That is, if you go, if you have this specific thing, then it is pure red. But if you have this specific vector out there, this is not really a pure red. It is red, but uh, not pure red. It has less of its white out there. What about brightness?
Brightness is intensity.
Actually, they are two different quantities. What is intensity? How do you measure intensity? How do you measure intensity with power, right? Watts.
Power.
When you
Watts.
actually, yeah, it's just the flux per unit area
Yes.
or volume. Depends how on which space you're measuring. So it's the power. What about brightness? Have you ever, any one of you ever read about the specifications of the screen, whether it's your mobile screen or your laptop screen or a monitor or TV? They say something, right? The brightness is this much out there. It's a basic unit out there. So there are seven basic units out there, right? Seven basic measurable things. So one of it is what? Luminous intensity. It
Mm.
is not the radiant intensity. Radiant intensity is measured in power, what we discussed just now. But luminous intensity is what is the brightness out there. What is the unit for luminous intensity?
Illumination lux.
No, no. I
Yeah.
said they're different, right? Flux,
Mm.
they are the radiant intensity. What is for luminous intensity?
Illumination.
Intensity is the flux part, which is measured power. What about luminous intensity? So, anyone heard
The
about?
exposure, amount of exposure.
No. Amount of exposure. It's okay. Given a camera, you might can define that
Yeah,
way.
yeah, in the camera.
I mean, that's not the usual way of defining. It's fine. I understand the intuitive idea. Anything else? At least any one of you remember the unit? So it is candela per meter square. Here is also power per meter square, watt per meter square.
Yes.
Anyone remembers candela?
Yeah.
Yeah.
Yeah, you have read those seven basic measurable things out there, which includes luminous intensity as one. So it is candela. Intensity is, since it's an intensity, you measure it per meter square. Luminosity is candela. The luminous intensity is candela per meter square. So of course here we are not so this is also called as nits. If you check any monitor rating, they'll give you 300 nits, 400 nits maximum brightness out there. So based on that, you can, if you actually want to, for instance, some people work out their work using their laptops on beaches, right? In India, it doesn't happen much, but in Western side, they take out their laptops in front of beach and work. So when so in that specific scenario, you need too much brightness out there, yes, so that you can cover the sunlight, beat the sunlight, and you can see the screen out there. But if you are working indoors, you don't really have to worry too much about sunlight. So there you will need you can manage with a uh, lesser bright monitor out there. So they generally the manufacturers generally specify it with nits, which is same as candela per meter square. I forget what nits is. Maybe you can just check it out. Okay. Keeping this aside, for our case, brightness is not really a concern for us. We are not. Uh, so we understood what the meaning of brightness is. We'll come back to the question. What about contrast? What is contrast?
Contrast is difference. I mean, um,
Minimum and maximum value
I
differentiation.
mean, how much
Maximum intensity.
differentiation
Yes.
Yeah. How much differentiation we can give actually? The,
Yeah, how easily you can identify, differentiate the grayscale
mm,
values.
yeah.
Grayscale value. Yeah.
Yeah. So if
Yes.
you remember this specific example, if you have some histogram like
Mm.
this, histogram means this is what frequency, this is gray value, which is R, if I remember correctly. This is again frequency. This has lower contrast than this. This is spread over a larger range, right? So this is low contrast and this is high contrast. Okay, so given this now, what are we mixing with white? What okay, when we are mixing white color with green color, what are we decreasing?
White color we are degree saturation.
Saturation. Yeah,
Saturation. Yeah.
this is the right. Okay, so is this part clear? This question. Okay, then
Yes.
move on to the next one. Okay, it's a big question to copy. Let me see how to copy. Okay, so okay, fine. So okay, so you're given that you're using some high pass filters, and if the cutoff distance for that high pass filter was 6 uh, in the units of frequency, then what would be the cutoff distance to obtain a second image? Okay, what is the characteristic of this first image? What are the artifacts that you see? Is there anything specific that you see in this image?
It is blurred. Reading
Blurred is okay, but not okay. Anything else?
the vertical bars are very clearly seen.
Okay. Can you tell me anything about the overall image? Not
Overall image is blurred.
blurred, okay, but anything more?
It's actually high pass filter is it's moved towards outside actually because it's curve. It is detecting curve more clearly.
So there was one specific term which I'm looking for, which we also discussed
Cutoff
at the start.
frequency moved away from,
Cutoff frequency is fine. Anything else?
yeah.
What is the
Yes.
artifact that you see? Do you see any artifact?
There is a ringing effect.
Yes, yes, that's what I'm looking for. Yeah. You can
Mm.
see that, right? If this is a block
Yeah.
out there, original block, you can see that it's being repeated. The whole image is kind of being repeated out there, as if it's centered from the specific object and then it's coming out like waves. So this is it has a ringing artifact. Okay, so this is a tricky question. So given this, so you have ringing artifact with cutoff of 6. Here the cutoff equals to 6. So what would be the cutoff distance to obtain the second image? The options are options. So I'll write it down because you have to just see the relative differences and the cutoff frequencies and not the actual value. Actual value doesn't really matter for the question I'm saying. Yeah. So here the cutoff frequency is 6. What do you think? So what is this new image? This is the second image.
Okay.
Second image has yes. So they obtained second image. So what do you think the cutoff difference frequency would have been?
Yeah, the second image they removed more low frequency, so definitely cutoff frequency is greater than previous one.
They removed more low frequency.
I mean, it means high cutoff frequency for the next high pass filter is greater than previous one.
Mhm. Yeah, greater than 6. Okay. Is it clear with everyone? So someone was saying like, yeah, although you have ringing artifacts, but what effectively is it doing? See, it's blurring up this whole region out there. See, you can't read A here, right? Or here or here.
Yes.
So it is effectively blurring out. So that means you want to just remove more of the low frequency part. How do you do that? By increasing the cutoff frequency. So this is what
Great.
low frequency part. So how to remove the low frequency part by increasing the cutoff frequency? How much will you increase? You said you have just 8 as an option. So if you use cutoff as 8, you can hopefully get this. Okay. Is this question clear? Okay, I guess we'll move on to the last question for our session. Straight lines are never straight. Okay, fine. I accept that. Okay, good. Here's the question. I hope this is okay. This is 2 0 now. Fine. So this is 1 of the was first part, and so here we are to the vector median filtering question. Okay. I hope this one zoom is fine for visibility. Yeah. So consider an RGB color image segment as shown below. So you have given one row of some color image, not even a row, 5 pixels of that row in the image, and then where each triplet location represents RG and B values, which is fine. The highlighted point, the specific point is corrupted by impulse noise. This is in wrong. Yeah. So this is corrupted by impulse noise. Okay, there is some noise in the input, it seems. Okay, I don't know what. Okay, fine. So I'll just explain it. I don't think I'm something wrong with the device. Yeah. Okay. Yeah. I'm back. So given that this pixel is with corrupted with impulse noise, you are given 3 pixels. You have to consider a window of 3 pixels and apply the vector median filter at the highlighted point. So which are the pixels that you will consider since you have to consider a window of 3 pixels? Anyone?
So we have to take a median.
Yeah.
Take
So
so previous
median
pixel
is
and
fine,
then
but first we have to define a window, right? So they said consider a window of 3 pixels.
yeah 3 yeah
So what are the three
x
pixels that you?
x minus 1 x plus 1
Yeah. So these three,
these three yes.
including the pixel at the query, which is the highlighted pixel. Okay. So we have this impulse noise pixel, and we have these three. So let me write this pixel as P1, P2, and P3, and the distances I'll write it as P1, 2, P2, 3, and P3.
Yeah.
Differences, uh, intensity differences. I'll write not distances. It's a wrong word. Intensity differences. Okay. Given this, what is P12? So it is. I'll just write the formula for the first one, so it's clear. 16692 square, 1890 square. We are taking the Euclidean distance, by the way. So that's why you're saying a similar formula here. So which is what? Uh,
0, 0. This is
66695 is
40 plus 95.
95. So
Hmm.
again, similarly, I P computed it. P23 will be 105.7. P23 means this distance between P2 and P3. And P13 will be what? Will be something near 17. Okay, P1 and 3. Okay, so now how to proceed with this question? I just computed distances. Why did I compute distance? Because we need to apply vector median filter, right?
Correct.
So what does vector median filter say? Choose uh, over the window, choose the pixel. This is the distance between this is x w y w, right? This is the pixels over the window.
Yes.
This is and this is x prime y prime. We are choosing this pixel. Choose this when it is the summation is less than summation taken over any other values gives you the least one. This is all pixels. Consider all pixels carefully. So this is the idea. So choose x prime y prime when they give the least summation value over the entire window. Least summation. Okay. So if this is given that this is the main idea of this, that's why we computed all P1 to P2, 3 and P1. Okay. So given this, if I choose a potential candidate as P1, what are the distances out there? Sorry, what are the intensity differences out there? It will be P12 plus P13, right? For P2, it will be P again, but whichever includes 2,
1, 2 plus
P12 plus
P2.
23, and P3 will be P12 plus P13. So these distances are symmetric whether you measure from 3 to 1 or 1 to 3, doesn't matter. So now we'll just replace the values. P12 is what? 95. This is also 95. 1317 and 12 is what? 105. Okay, I'm just leaving out the decimal places because here they don't matter much.
Hmm.
Yeah. So P1 to P13, this gives us 112. This is 200. Oh, sorry, 122. Yeah. Okay. So now which pixel will you choose? Which pixel value will you choose?
P1.
P1.
P1. Yeah. So you replace the highlighted pixel with value at P1. Yes. So the final answer would be whatever P1 has. 160, 80, 40. Okay. Any doubts?
Hmm. No, sir.
No, no, sir.
Okay, then I guess this was a bit longer session. Anyways, I think we are done for today. Okay, then. Thank you guys for joining. We'll see you
Thank you.
next week, same time.
Thank you.
Okay,
Bye.
bye.
Bye. Thank you.